Hi everybody, welcome to today's lecture. We are going to be talking about Unix, and we're going to introduce the operating system itself. We're going to talk a bit about its history and how we start to use this operating system. That's important because since Unix is our model operating system that we'll be studying for the entire term, we're going to want to make sure that we understand how it works internally. But to get to that point, we're going to have to know how to use it. So this is our introduction to the history of it and our introduction to how to start to use it. So let's look at the history first. All the way back in 1965, before I was born, AT&T, Bell Labs, MIT, and GE, General Electric, they started work on a joint project, and they called it Multics. And Multics stood for Multiplexed Information and Computer Services. And it had a few different things going for it, which were pretty novel. So first of all, it was the first operating system to have a hierarchical file system, which meant files and folders. Such a thing had been discussed before, but Multics was kind of the first stab at it. As a time-sharing operating system, that means that it could achieve what is called apparent concurrency. It could run one process for, say, 10 milliseconds and then switch to another process and run that one for 10 milliseconds. By switching between processes fast enough, it appears to the end users that all of those processes are running at once. That's time sharing. So these three companies, these research labs and companies, get together to work on Multics together. From the MIT side, their development was led by Fernando J. Corbato, and there were lots of different wonderful guys and girls involved in producing this entire thing. So 1969, by the time we get to here, the project fell apart. Bell Labs management pulled out due to delays. The Bell Labs researchers were really the core researchers involved in the effort. And when they discovered that they weren't really being met from the other companies by the same type of progress, or certainly not the same fervor with what Bell Labs wanted to do, Bell Labs pulls out. So they were employing some famous, well, today we would call them famous engineers, Ken Thompson, Dennis Ritchie, and some others that are less well known, Rudd Cannaday, Doug McElroy. They were all still invested in this project. They'd put a lot of time into it. They decide that they are going to continue working on this on their own. So they call their version Unix, which is a play on the other spelling of the term Unix, because theirs is kind of a cut down, if you'll forgive the term, version of Multics. They called theirs a Uniplexed Information and Computer Services operating system, or that's what its name was. And they were doing this on what's on a PDP-7. So here is an example of a PDP-7, and you can see that these big blue things are really just cabinets for storage, but the actual computers here with their reel-to-reel recorders and levels and oscilloscopes and all kinds of crazy stuff that it took to get these things wired up and working. Over here you can see there's a teletype or a keyboard where you can enter information on, but there's no readout that tells you what you're doing. So they were pretty primitive. Impressive that they were able to do so much work on it. This particular one is a PDP-7 that they are trying to restore. I think it's in Norway, I think. By the 70s, January 1st, 1970 becomes what's called time zero for the Unix operating system. We call that sometimes the beginning of the Unix epoch. That particular date is used as the base, and then we count forwards from there. By the time we get to the 70s here, the early 70s, we've got text processing abilities that have been added, and that allows Unix to start being used for actual work by other groups at Bell Labs. So in this picture here, we see Ken Thompson sitting. We've got Dennis Ritchie in the back, and they are working on this system. You can see that the computers they're using are fairly large, lots of tapes that are being held in place. And check it out here. Ken Thompson doesn't really have a display that he's writing at. He's just entering in characters. So pretty hardcore, pretty old school. This particular one, they're running now on a PDP-11/20, which was a faster computer, better than the PDP-7. So the first manual that was produced as an online man page was November 3rd, 1971. And the man pages are a series of, manual pages that describe how the various programs and utilities in Unix work. They are notorious for not being tutorials. They don't tell you why or how you would use a tool. They tell you what the tool does. So they put together these things onto these man pages and started to spread the knowledge of Unix. By the time 1972 comes around, they decide that the languages they were using are no longer sufficient. They were using B and some other stuff, a lot of assembly. So Dennis Ritchie takes it on himself to write a new programming language, and Dennis Ritchie writes C. So the C language that he develops is what they start to write Unix in. So we see this in a lot of cases with Unix development, but the development of Unix and the development of C go hand in hand. There are similar utilities, similar tools, similar abbreviations that we'll find in both cases, and that informs us as to how to use each of the two, because we know the C version might tell us about the Unix version and vice versa. They present their Unix operating system to the outside world finally in '73 when they go to the ACM, and they report this at the Symposium on Operating Systems Principles. They couldn't yet turn it into a product, into a commercial product, and part of that was because in the 70s, through the whole 70s, there was some antitrust regulation that was moving its way through the pipes, and eventually this sees the splitting of Bell. So it gets split into all kinds of different companies all over the United States. So Ma Bell gets split into, AT&T and Bell Labs, and a lot of different groups have their own territorial telephone company now as the United States government breaks up Bell. So because of all this was happening, they couldn't turn this thing into a product. Plus they had agreements with other companies that they were working on. They were doing this as kind of an educational thing. So Linux then was developed by Linus Torvalds. So as Unix is being developed here, the kernel of it, that is all of the different little programs that are used to drive the operating system and tell it how to access memory, tell it how to access the hardware, and that contains all of the utilities that are essential to the core running of the operating system, that kernel cannot be shared. There are license agreements in place. However, if you copy the form of it and the effect of it and then give it away, you're not breaking any laws. And this is what Linus Torvalds does. He develops his own system and calls it Linux after his own name. And he does that to break out of the license agreements that are protecting Unix, and he releases it as an open source product. Everybody can change it and access it and do whatever they want. So he also adopts the POSIX specification. What POSIX does is it allows, if you're following the POSIX specification, it means that your programs should be runnable in other POSIX-based systems. So Unix, Solaris, HPUX, Intel's AIX, lots of others, they shouldn't need many changes to run on each other, including Linux. So while the servers that we use here in our course are all Linux-based, that same knowledge is applicable everywhere. In fact, you'll hear me move interchangeably between Linux and Unix. They all mean the same thing at the level we are talking about. Linux is very stable, it's very robust, and it's free. And it's a fantastic educational tool because we can see the insides of it. We can see any of the source code at any time. First version of Linux came out in 1994, so March 14th, 94. You can run Linux at home. You might already be doing this. It's easy to grab. Lots of different distributions are out there. And the distribution is where you would take, say, the kernel that Linus wrote and then bundle it with a bunch of other tools as a full-featured operating system. So some of the more famous ones would be Ubuntu and Debian and Red Hat. And nowadays we have things like Mint and Arch Linux. So lots of great distributions out there. They can all be downloaded. They're all free. Support for them is sometimes something that's purchased. So there are purchasable versions, commercial versions of these operating systems, and that's just fine too. For our purposes at EECS at OSU, we have lots of different Linux machines that you can connect to. Alright, so distributions get created with different purposes and features in mind. We don't just have a distribution that works for all general purposes. We create that distribution for a certain purpose. While Ubuntu was designed from the ground up to be easy to use, Arch Linux is the opposite. So it's going to require that everything gets installed manually. The Tails distribution is built to be private from the ground up. So that means that there's a lot of incognito tabs by default. There's a lot of tunneling and VPN systems that are integrated into it. Lots of different features go into different distributions to separate them from each other and provide different services for the end user. So how do we actually interact with Unix? Well, modern versions of Linux all have a graphical user interface, but we're going to be looking at things a lot lower. So we actually don't touch any GUIs, any graphical user interfaces at all in this course. We'll be using just the command line. So the interface to the operating system is this command line interpreter, and it's also called the prompt, would be another name for it. And from the prompt, we have access to all of the Unix user level programs. So we can start things up, we can manage processes that are running, which is called job control. We can connect the processes together and they can communicate amongst themselves. We can manage input and output to and from those programs, and then we can terminate them. And we can do that from the shell. So the shell is our user interface program to the operating system. The shell is a piece of software just like any other piece of software. The difference is that the shell has been written such that it knows how to talk to the operating system directly, which our user programs cannot do. So the shell prompt itself is traditionally done as a little cursor, and you can move that cursor around and enter characters, and they're all displayed on the screen. And you can customize that thing. So here's a few different examples. This one I've got. This is the one that I'm currently using. 1459 is the current line that I'm entering here, and here's my username on a particular server, and the tilde represents my home directory. So here's another version of it, and this one has the time of day integrated into it, and this one has the current directory that I'm in as part of it. So you can change what the prompt of the shell looks like to match whatever you want. The $sign at the end is the traditional symbol for bash, the particular shell bash. So to create different types of shell prompts, here's a great website, easyprompt.net. The reason why doing this from a website's a good idea is because the actual strings that it takes to make your shell look differently are pretty complicated. So for example, this is the line here that it takes to create a different shell look. So PS1 is the variable that you're going to put this prompt into, but look how complicated it is. It's got all kinds of escape characters and special symbols that do different things. And without having a giant dictionary or websites online that tell you what to do, it's very difficult to write. So I like this website just because I can enter in I can drag and drop what I want, and then it tells me the string to use. Once you have that string, you can put that into your .bashrc file, which is in your home directory, or at least if you're using bash, this is where you would place that. And that way, the next time you log in, you'll have the shell. The prompt for your shell looking however you like it to. Let's look at some examples of running programs. So if you've used Unix and Linux before, this is going to be really basic, but bear with me, we need to get everybody to the same level. So here I'm going to run the ls program. We'll talk more about ls in a minute, but ls just says list all the files. And when I hit enter on that, type ls enter, it then spits out the current files that are in that directory, in whatever my current working directory is. Now, we don't get much specificity out of what these particular files are. Are those files? Are those directories? Are they executables or not? So having something that gives us a little more options would be good. So if we add a command line switch, if we add a switch to the ls program, this one here is the -a switch, that means list all the files, including the hidden files. So a hidden file is merely one that starts with a period. So .bashrc now gets returned. We can also see that there are some other special things that aren't really, well, they are files, but they're special files that are used by the shell to change the working directory. So the dot refers to the current directory, and the double dot refers to the parent directory. And we'll look at some examples of that coming up. So different Unix shells that are out there. The original one would be the Bourne shell, And the Bourne shell was written by Stephen Bourne, and it was just called SH. And that itself was a replacement for Ken Thompson's original SH shell, which was based on the SH shell from the Multics project, from the failed Multics project. So the one that we use in this course is Bash, which is an upgrade to the Bourne shell. I would say probably the most other famous shell out there is the C shell, which has a lot of C programming-like syntaxes and familiarity to it, but I think that Bash is the better shell. These enhanced ones include certainly Bash, the TCSH enhanced C shell, sometimes pronounced teach. The corn shell is another one. There's other ones out there, the Z shell. There's tons of different shells that you can use to interact with the Linux operating system with. Again, we use Bash. Okay, so some common Unix commands. We'll talk about a lot of these over the course of the term, but just to get you familiar with what they look like and what they're called, you can see that for the most part the vowels are all gone. It's like a wave came onto the boat and washed all the vowels aside. So you kind of have to guess and learn and memorize what these things do, but CD stands for change directory. PWD is print working directory. We've already talked about LS for listing our files. This is make directory, remove a directory. This is move, which is also used to rename files. This is copy. This is remove, so RM for remove instead of delete. LN is used for linking files together. That's like creating shortcuts from one file to another. And chmod, or chmod, is change mode, and it's used to change the permissions involved in accessing a file. For file viewing and editing, we have things like cat, which is short for concatenate, the more and less pager programs. We'll talk a lot more about these. Head and tail for extracting lines from output, and grep, which is used to filter out lines, and cut to remove columns from files. Editors you may or may not have heard about are VI. We've got a whole lecture coming up on VI. Emacs, there's traditionally been a holy war in editors in the Unix world. The VI people fight against the Emacs people, and they try to convince the others that theirs is better. There's simpler ones out there that are not near as powerful, but certainly can be used, Pico and TextEdit among them. Some other commands that we use are scripting languages, find for locating files, the telnet program itself, SSH for doing a secure connection, and a ton more. All right, let's look at some of the most important ones here for moving around. So PWD and CD. So PWD for print the working directory is the where am I command. So it lets you know at which hierarchy in the directory structure you are. You can add this where am I functionality into the prompt itself, as we showed above in some of those prompts, but traditionally it's not part of what you see. So you have to use PWD to see where you are. CD is used to change your current working directory, and it'll allow you to move directly to an absolutely specified directory, or you can move relative to where you are. So let's look at a little example here. So at the top line, I type CD ~/cs344/program1. So the tilde is a shortcut to my home directory. So it says, all right, I want to go to my home directory and then down into a directory called cs344. And note, Unix, Linux, all these are case sensitive. So capitals are different than lowercase letters. That is not the case in Windows. In Windows, they are treated the same. But in Unix, they are very, very much treated as separate characters. And then inside cs344, I want to go into my program1 directory. When I hit enter on that, note that I don't get any output. Nothing says, hey, that succeeded, or hey, that failed, or anything. It just gives me the next prompt. So I type pwd to say, okay, where am I now? And it tells me I am at /NFS stack faculty B brewsteb cs344 program1, which is where I want to be, because all the rest of this, NFS stack faculty B brewsteb, that is where my home directory is. The slash at the beginning here, that's the root of the entire directory structure, and if we specify that, that means that we're giving an absolute directory path. Same thing here with tilde. Tilde is an absolute directory path because we're saying I want to start at my home directory and then descend into other directories. Alright, so here is a relative directory movement with cd. I'm cd ... which means go up a directory level. When I do my print working directory from there, sure enough, I'm now not in the program1 directory, I'm up in its parent, CS344. I can cd directly to tilde, which is a shortcut for my home directory, and the PWD of that shows me that I am in fact at my home directory. Let's look at ls here in a little more detail. So what ls does is it's going to display all the files in the given directory, and we can specify which directory we care about, and we'll look at some examples of that through the lecture here. It'll accept both relative and absolute arguments in terms of displaying which directory you want. In the examples on this page, I am not specifying a directory to display, which means that ls simply displays the current working directory. So here when I say ls, it returns to me CS344, CS464, and something called PID test. But what are those? We need some more options to figure out what those things are. So here I'm going to add the P, L, and A options to the ls program. So one thing I want to note about this little hyphen character here, that hyphen character isn't part of the shell. It's not part of Unix. That hyphen character is something that the ls program is looking for. So as in, the authors of the ls program made it such that the options that you would pass in have to be preceded by a hyphen. But that's not part of Unix or the shell. That's just the way the ls program operates. If you used a different operating system, one called BSD, a lot of the options in BSD don't use the hyphen at all, so they're just specified as raw letters. So different operating systems, different ways to do it, but here on Linux, most of the utilities have a hyphen in the front of the command line switches. And you can combine them together by just putting them next to each other. You can also split them out, so you can do -P, -L, -A, that kind of thing. It depends on the utility for whether or not that works. Anyway, PLA, what do? The A we talked about before displays all of the hidden directories as well, so we'll see the dots and the double dots in the hidden files like bash rc. The L gives us the long form. That's what's making it be so that we get all of these details about each one of these entries, each on its own line. The P is what is actually all the P does is it adds the little slash here at the end of the directories. So it's a way to show us that these are directories and that these other things are not. So .bashrc is a file, PIDTest is a file, .double dot, and these two CS directories are all directories because of the slash. In the old days, that was how you would have to tell just looking at the names of them. And if you can look all the way on the left, these little D's here also indicate that they're directories, which is kind of nice. Nowadays, we have color displays. And if I add this extended and long option, -- color equals auto, it colorizes things, which makes it a little bit easier to see what they are. And here, we could maybe take off the P argument such that I could tell the difference between a directory and a file just by seeing blue versus green. But I like the slash there, and it looks like a directory when it's got a slash. Alright, so it's a pain in the neck to type ls space -pla space -- color equals auto every time I want a nice ls output. So a program exists, or utility exists, called alias. And what that does is it lets us set a variable or a command or a piece of text to be a longer version of it. So in this case I'm saying I want to alias L, just L, and set that equal to all of this text, such that whenever I hit L, I get the long form of this. And here's an example. Here I type L, hit return, and there's my ls -pla with the automatic color. So much, much handier to do it this way. Some of these other commands: make dir for creating directories, remove directory for deleting directories. rm is for deleting individual files, and is also, confusingly, the tool that you would use to delete directories if you run rm in its recursive mode. mv is for moving and renaming files and directories, cp for copying. Let's look at some examples of this stuff. Alright, in this example here, at the beginning, we're first going to run make dir to create a directory called tempdir. So make dir tempdir creates a temporary directory. Now note, we don't get any output out of that. It's just tempdir, and then we get the next prompt. Next I'm going to run a command that says touch my file. What touch does is it either creates a file if one wasn't there by that name, or it updates the timestamp for that file to the current time. So it's a way to reach out and touch that file to say, yep, hey, I've modified this file, or I've accessed this file. It's a way to manipulate which ones you're working with, say, if you're using other programs that rely on knowing when files got touched. But in this case, if the file doesn't exist, it's a handy way to create a 0-byte file. Then I'm going to use the mv command to move this my file that I just created into the temp directory. Now remember how we talked about how mv is also rename. So how can you tell the difference between whether it's moving versus renaming? And in this case, it's because tempter, the second parameter in this line, or the second argument, is an existing directory. So since mv sees that, it says, oh, I'm not supposed to rename my file into tempter. I'm supposed to move my file into the temp directory. So that runs, and we get no output, so we assume everything worked. Then I cd into tempter, again, no output. I set the alias, because I don't want to type all that for ls every time. And then I run l. When I do that, it shows that I am in a directory that contains only my file, and that it's 0 bytes. That's perfect. That's just what we'd expect. Now I'm going to copy my file into a new file name called myfile_backup. Then I'm going to remove the original my file. And in this case, it prompts me. It says, rm, remove a regular empty file, my file, and then it asks for yes or no. So here I say yes to go ahead and delete the file. Now normally, remove just blows away the file without asking. But there is a switch you can give to rm, which is the -i switch. And it turns out that there is an existing alias that that OSU adds onto your rm command, such that whenever you type rm, it substitutes that for rm -i, just so that it can ask you to delete files every time, or just so that it asks you for confirmation for deleting files. It's a really handy way to protect you so that you don't delete things on accident. Alright, so then I type ls, and it shows me that sure enough, the only thing in here is my file backup file that we created. Now I'm going to move my file backup to my file. Now since the my file no longer exists, I am renaming this file into that one. And since that's not a directory, this is accomplished as a rename. So when I do the ls command, I sure enough see just that file. Then I can copy my file up a directory level to the directory above with a new name. So copy my file, make it a file called new file at the parent directory, cd back up to the parent directory, list all the files that are in there. I've got new file and the tempter itself. And there's that new file that I just created. Then I'm going to remove the temp directory, and when I try to do that, it says, oh, can't remove it, temp directory is not empty. So remove dir is not your tool of choice here. I instead use remove directory with the recursive option, which says delete the directory and delete all files that are in it. The F switch says, don't ask me, just do it. And I specify tempter as the target, and no output, because it then goes through and deletes all the files and directories inside tempter, and then returns. So there's an example of moving around and creating directories and creating files. Let's take an aside here and talk about input and output to and from the screen. So the shell itself is going to open up the terminal as the target for reading from and writing to. And the way it does this is that anytime a command runs, that command automatically has 3 files that are open in that program. So when you run ls, ls comes into existence and has 3 files that are automatically ready to go. And they are called standard in, standard out, and standard error. And they're abbreviated as standard in, standard out, and standard error, just as you can see there on the screen. And they have numbers. They have a file descriptor number, and we'll talk more about file descriptors when we get to C, but they have file descriptor numbers 0, 1, and 2 respectively. So these files that are open, they're kind of a pseudo file stream thing that we'll talk more about later, but think of them as files. These files that are open inside that ls command that we have run are pointers to other files in the operating system So I can send something to standard in, but standard in itself can be redirected to point wherever we want it to. By default, standard in, standard out, and standard error are pointing to the terminal. So you call ls up and running, and then if you told ls to get information from somewhere, it would by default get it from the terminal. And when ls output its data, it sends it to standard out, which by default points to the terminal. So the point of this is that if you don't specify otherwise, program input and output goes to and from your shell prompt to the terminal by default on every line. The reason we bring this up, of course, is because we're going to change this. We're going to start to manipulate the input and output with the next bunch of commands that we use. So starting with echo. What echo does is it sends character data to standard out. What echo does not do is send text to the screen. That's not what it does. Echo sends character data to standard out. So if I just use it by itself, I say echo text, then echo as a command takes text as an argument, slurps it into itself, and then sends it to standard out. Standard out points to where by default? The terminal, so it's displayed on the terminal on the next line. Text. There we go. Then I can say echo test text, and it's able to take all of those different arguments and combine them into one long string and output that all to the terminal as test text. This next version here, I'm using the -e switch with echo. And the reason I'm doing that is because when I use -e, it's going to interpret the special character \n as a new line character. So I can say test text, new line, next line. And incidentally, this \n is a single character when it's represented in the file. It's displayed as a line feed carriage return new line thing, as you can see here, but in the actual file, in the actual characters that are stored, new line is a character, just like an A is, just like a Q is. Okay, so with the -e, I can interpret that \n as a new line, so my output is what I expect. So echo sends all its data to standard out, and since standard out hasn't been changed away from the terminal, then all of the data goes to the terminal. Okay, so cat. Cat is a separate utility that concatenates files together, concatenates character data stored in a file, and then it sends its output to standard out. And again, standard output points to the screen typically, so that means that you take a bunch of files, concatenate them together, and send it to the terminal. So cat file1, and note I didn't give it anything else, and that tells me the contents of that file, which are in this case just file1 contents. I can say, all right, let me concatenate file1 and file2 together and output those to the terminal, or to standard out, which points to the terminal. And it tells me, sure enough, here's the contents. File1 contents concatenated with file2 contents. That's my output. So since it wasn't explicitly changed, everything goes to the screen. All right, let's look at redirecting now. That is done with this operator. This is the open alligator eats. This is the greater than pointing to the right operator. However you call it, this little angle operator tells standard out to instead open a different file for writing to. And this is going to affect the entire line. So this modifies standard out to point to a file instead of pointing to the terminal. Now it's important that whenever you see this operator, you realize that it means a file is about to be the target of the operation here. So here I'll run ls. Note that ls returned nothing, so there's nothing in the current directory, or at least no non-hidden files. Then I'll run an echo -e with this as the argument, so cookie, new line, beefcake, new line, apple, and I'm redirecting all of that to a file called foodlist. So the standard out gets redirected to open a file called foodlist in this case. Then when I run ls, again, there's a new file called foodlist, which was created by my echo command. I can cat out the contents of that, and I get exactly the contents I put into it: cookie, beefcake, apple. So in this cat command, there was no redirection that was done, so the terminal was open for writing inside the cat command. That's where standard out was pointing, so that's where the data was sent, and it's pointing at the terminal, so we see it on the terminal. Let's look at the sort command. So the sort command is going to take data from standard in, or it will take data from a file, and then it sends that data alphabetically sorted by line to standard out. Alright, so let's set this up. I'm going to use my echo -e command here to create cookie, new line beefcake, new line apple, and store that in a file called food list. Then I'll cat that food list file out just like we've seen before, and then I'll run the sort command. Here, sort, and then the file I'm giving it is food list. So the sort command opens up that file, extracts all the contents, reads them into itself, sorts them line by line, and then outputs those lines to standard out, which points to the terminal, and there we see the information there. So this was me running sort, grabbing it from a file. Sort can also grab the information from standard in itself. So here is the same command we just saw on the previous screen, where sort is opening up a file, reading it in, sorting it out, and sending it to standard out. But in this version, what's happening here is that the sort command is simply invoked, and it wasn't given any arguments, and it has no concept about the things that are happening to the right here. So what sort does is, since it has no argument, since it was given no argument about a file, sort goes to read from standard in. That's where it goes. It goes to this pre-built file that it has called standard in and opens it up and tries to start reading data from there. Now, fortunately, we have provided redirection to standard input from a particular file. So here is a new operator. This is the one that points to the left, and this particular operator, the less than operator, say, is indicating that it is opening up a file called food list and providing that as standard in to the command sort. So the output is the same, but how it happened is very different. Our usage of sort here, sort looks to standard in for its input. And how did that input get there? Because this operator opened up a file, extracted the contents, and caused that to become standard in for the command to the left. So we can do, let's take a look at what happens if we try to read from standard in and we don't have any redirection set up. So this is the redirection symbol for the standard out, but I don't have one here for standard in. So the concatenate command attempts to read from standard in, but has no data. We didn't redirect anything like we did on this slide, where we have the less than operator. We just have no input given at all. So what happens is that it tries to open up what it has, which is the terminal. So it opens up the terminal for getting data from. Now the terminal doesn't have any input either, because the user provides input to the terminal, so the little cursor just sits there blinking, asking you to type something in. So you start entering in your lines dutifully one by one, and hitting enter every time just advances the input on. That's just giving it new lines. So what Control D does is it sends essentially an end of file character, and when that is read by concatenate, it says, oh, there's no more standard in available, and then it finishes doing the rest of its command. In that case, it is take the input that I have and send it to standard out. So in this case, standard out has been redirected to a file called list, and when I then cat that file list out, I get the contents. So kind of a complicated usage here, but we are going to use this in program 1 in order to easily capture data from standard in. Let's take a look at redirecting both standard in and standard out at the same time. So at the top, again, we define our food list file in the same way we have before, and then I'm going to run the sort command, where I grab where it is going to try to grab data from standard in. And where does that standard in data come from? From the food list file, which has been fetched by this less than operator. And the output of that, of course, is sorted data. And the next line, I combine the two. So I run my sort command, and I indicate that the input comes from a file called food list, and the output should go to a file called sorted list. And then when I cat sorted list out, I get the output. Now note that when I ran sort here, there was no output to the screen at all. That's because we captured the output and redirected it to a file instead of redirecting it to the screen. So this whole big complicated sort line has no output to the screen at all. We can only see the fruits of our labors by outputting the file that was resulting from it. Now one thing that's important about this is that the order of these two modifiers to the sort command doesn't matter. from the perspective of sort, sort has no arguments. So sort thinks that it was invoked by itself with no arguments, which means it's going to try to go to standard in, standard out, and standard error, which we haven't talked about much, but that's okay, we'll get to that one later. It goes to those three files in order to do what it's supposed to do. So down below, we show that difference. In fact, I've even collapsed out the space, which isn't necessary, just to try to show you. Here's the sort command being invoked, and then as a modifier, I'm saying all of its standard out should go here, and all of its standard in should go here. So it's not like this is being read from left to right, like some sort of flow from left to right. This is the sort command being modified in a few different ways, and once those modifications have all been read in by the shell and operated on, the sort command is launched with all of these redirection modifiers in place, and then it runs and does what it's supposed to. There's a bunch more examples about this available in the articles online. Okay, so shell file name expansion. So certain meta characters are going to be expanded and replaced. In this case, when we're at the shell and I use the asterisk, this isn't really regular expressions we're talking about here. This is what's called file name expansion. So the asterisk says, take the string that I'm entering that has an asterisk in and match anything, and it will actually return all of the matching file names as a result. So it kind of expands and explodes a term into lots of terms, which are then interpreted by the command that you gave it. And we'll show an example of this in a sec. The question mark, on the other hand, matches just one character, whereas the asterisk can match any number of characters. So again, not regular expressions. This is just part of bash, part of the shell here. So top example, we're going to ls, and here we're actually specifying the directory that we want to get a listing of. So here, list me all the files in any directory whose names begin with CS344, and then any number of characters afterwards. So that certainly would return things that are in CS344, as well as stuff from directories that had any more characters there on it. In this next example, this is saying, return me all the files in the directory that have CS344 somewhere in it. So there could be characters before, there could be characters after, but this is distinct from the first one because before we were saying it must start with capital CS344. Okay, down below we're adding in a subdirectory. So here's a kind of a multi-line example. In our first line, we're creating a directory called CS344, and then in that directory we are touching a file. We're creating a file. So note the semicolon here means I am going to have multiple commands all on one line. The touch command is being given a file path which is inside a directory, and it ends up creating this file in this directory that we just created. Then I'm going to run it again, but this time I'll put a 0 at the end on all of these, and then run the same make dir touch commands in sequence, but this time with a 0,1 at the end. Then I'm going to run an ls command that says, all right, look for any subdirectory give me all the files in any subdirectory that begins with anything but has CS344 in the end and only one character at the end. And the only one that matches that is the file called file in CS3440. Okay, so before we talked about how you're not supposed to read these things from left to right. Well, pipes is where we are introducing flow from left to right. What pipe does is it gives us this way to communicate from one command to another without using a temporary file to hold data, as we've been doing up till now. So here's an echo command, echo -e, create the same data we've done before, but this time the pipe operator says, take the standard output coming from that echo command and redirect it to the standard in of the next command. So here, the sort command gets invoked with no arguments. So it doesn't have a file that it needs to read from, so it tries to grab data from standard in. And fortunately, data was provided from standard in by the echo command. So here, by taking this echo command, piping it through sort, I get a nice sorted command. So I can take my echo command that I've been using this entire time, and with a simple pipe sort at the end, I get to sort all of my data. Really handy. Let's do this, a couple more compound commands here. So echo -e, cookie beak fake apple. This time I'm sending this to a file called food list. Then I'm going to cat the food list file out, and piping the result of that into the sort command, and I get the same thing again. So I can use my pipe sort little trick here on either files. Well, it only operates on standard out, right? So that standard out has to come from a file, in this case cat food list, or it can come from a command like echo. But in either case, the data arriving into the pipe operator is data that hit standard out from a previous command. Okay, down here I have cat food list piping into a sort command. So don't be confused by the fact that here's an operator and here's our operator, and where's the break? The break is at the pipe operator. That is absolutely where the break is. Cat food list is one command, and its data goes to standard out. Pipe operator takes that standard out, redirects it to the standard in of the sort command, which didn't start with any input, so it goes to standard in to read from, grabs the data, and then sends all the output to sorted list. Then I can cat out sorted list to see what we have. We are going to use pipes like crazy in this course. The more command is it's a program called a pager, which takes character data and displays it one page at a time, one screenful at a time. And while you're spacing through all these different pages of really long output, you can navigate up and down with up and down, but traditionally you just hit spacebar, spacebar, spacebar to advance down through the pages. And if you don't want to have to spacebar all the way down through to the end, you can use Q to exit out of the paging that you're looking at. This is what looks like a double standard out redirect operator, but when they're combined like this, this is the append operator. So instead of overwrite, which is what we had before, this is the append data. So when there's just one of them, that means redirect to this file, and by the way, if there's anything in that file, delete all that information and overwrite it with what I have. So, not just overwrite the first line and leave the rest there, but no, first delete all the contents of that file and replace it solely with what I'm about to send you. The append operator does away with that and just adds the contents to the end of the file. All right, so a little example here. Here we have a shell demo script where I am echoing a line that has multiple new lines in place to a file, and then I'm going to append a lot more numbers, each separated by new lines, to the same file, and here is that little append operator. Then I'm going to do it again with even more, again appending them all. Then I'm going to cat that row file out, which is a very, very long file now, pipe it through sort minus nr. So what does that do? Well, the n switch is going to do a numeric sort instead of an alphabetic sort, and the r is going to do it in reverse order. And I'm going to take that whole thing and append it to row file, and that gives me this same information now reversed, appended to the end of my row file. Then I can cat the whole thing out, and then I can cat it out and push it through more because that file is really too long in the first place. So let's do an example of this. All right, let me reach over here and grab my terminal display. There we go. All right, so let's do an example of what we're talking about here, and I'm going to kind of shrink this a little so I can type some of these commands in. Let's see, grab, shrink, there we go. All right, so echo minus E, and we don't have to do quite as long as the one we did down there, but let's go minus E at 1, and then with \2, \3, \4, oops, I gotta have an N. There's my N, \4, \n5, end that string. We'll talk more about quotes here in a coming lecture. Redirect all that to row file. All right, so that's all now in a file called row file, and I can cat this thing out. So row file, there it is. Oh, look, there's that extra 4 that we've got in there. So if we want to change that here, I'm going to use the up key, and when I use up, it shows me previous commands that I've run. So I can go over here and I can find that /4 that isn't supposed to be there, rerun the command, and you'll see that this time it blows away the command that I just ran. Let's see here. Echo row file. I want to cat this thing out, keep pushing up. Oops, wrong direction. Cat row file. There we go. So now I can push up and I can execute the same thing. You can see it's been replaced. Okay, so now let's go ahead and add some more to this. So echo minus E. Let's do 6, new line, 7 new line, 8 new line, and this time we'll append to row file. Now I can cat row file, so I just push up, cat row file, and there it is. We can see the 7 and the 8 have been added. That's nice. And look, you can see there's a new line at the end there because I added one without a 9 at the end. So now what we're going to do is we are going to cat out row file, and we're going to pipe this thing through the sort command. And I will do a reverse numeric sort, and I want to append this back onto row file. So run. So no output on that because I've changed where all the output goes so that it's redirected to a file. Now I can cat this thing back out. And there it is. You can see that we've got this whole thing repeated and then reversed and appended to my files. So that actually works pretty well. If we do the same thing again, then now we have a much longer file. So if I run cat row file, we have a very long thing, and you can see we started to double up a lot of the numbers because we're combining things. And now I will cat row file, pipe it through more, and we can see the result of having all of this be concatenated at one time, occupying multiple pages of screen text. So space bar through to get to the next one. Okay, let's take a look here. We are going to move to another example on this shell script here. I'm opening up here my cheat list on my other screen. All right, so let's open this thing up. There we go. We are going to pretend that we're in a new bash shell. So if I type bash, that does start up a new bash shell. It's hard to tell the difference, but I am in a new bash shell. I can clear the screen to get to give myself a nice clear prompt at the top. I'm going to echo out some text. In this case, I'm going to do the same cookie, new line, beef, cake, new line, apple, text that we've been doing before. Send that into food list. Then I will echo out, let's do here, dog, fish, and eel, and I'm going to put this thing into fish list. Okay, so run ls, and sure, got a lot of different stuff in this particular directory, including fish list and food list. We can cat the two out together, so cat food list, and here we'll put fish list on the same one, and there's our output. Definitely not sorted. If I try to do something like this, I want to show you the result. There we go. So what I'm doing here is I'm saying sort, grab standard in from, and then I'm passing it a command instead of a file. And this doesn't work because the operator here, the little less than operator, tries to open up the next thing as a file name, and cat isn't a file name, so you can't string commands like this together. This operator always wants a file name to be the next thing. So let's look at a different way to do this. I'm going to cat food list and fish list and push those into a file called, that should be one of these, into a file called big list. Go. And then I can cat this thing out, and now I've got all that data stored in a file, unsorted. I'm going to run my sort command where I take that as input, and I provide as output sorted big list. Run. And now I can cat out my sorted file. Note that I'm going to type this much and then hit tab, and it will auto-complete the only matching name of the file in the directory. That's a handy thing. Hit return, and there is my sorted file, A, B, C, D, E. So let's reverse sort this thing. So I'm going to take sort minus R, and I'll say this time, I'll do it the other order here. So here we'll say that my output will be, and I'll use a space just to show you that there's lots of different ways to do it. Sort to reverse sorted big list, and grab the input from big list, run, and then I can cat this thing back out, cat rever tab to see the rest of it, hit return. There's my reverse sorted list. Okay, if I cat out a whole bunch of these, I can cat out all of the files that begin with list. I can do that twice to give myself a whole lot of files at once, pipe all of that through sort, and then pipe all of that through the more command, gives me a lot of different, well, apples, beefcakes, cookies, dogfishes, and eels. And I can space my way through all of those. And note that that was all just sent to standard out. I didn't try to put that into a file, but we could have. We could take all those things and put them in a file if we wanted. All right, well, I hope this has been an interesting introduction to you to learn about how Unix works and how we can interact with the operating system. We've got a lot more lectures coming up about how to do this before we start diving into programming it to do more operating systems-y type of things. One of the paradigms that we see in Unix a lot is that we string together small programs to do big things. So that principle is illustrated by using pipe to combine the effect of small programs together to build something up as a larger whole. Our first programming assignment does just that. All right, we will see you at the next lecture. Thanks a lot, everybody.